Alrighty, welcome to this video on Boyles' Law and Charles' Law. And don't worry, whenever I see a law with a dude's name in it, I always get scared and think it's going to be extremely complicated. But we'll show you that Boyles' Law and Charles' Law are actually very simple laws to use to understand and to apply to equations. And the first thing to understand about these laws is that they are both gas laws. So this unit is all about gases, if you haven't figured that out already. And so these are just gas laws. And whenever we have a gas law, all we're trying to do is relate three different quantities together. Those three quantities are pressure, volume, and temperature. And you guys are all smart. You know what these things are. I don't need to define them for you, but I will. Pressure is just the force exerted on the walls of a container by a gas inside a container. Volume is just the three-dimensional space a gaseous system takes up, or a gaseous container takes up. And temperature, well, you know what temperature is. And so, to begin, we'll take a look at a sort of a qualitative understanding of Boyle's law. And to do that, we're going to take a lake that's constant in temperature throughout. So all this water is at the same temperature. It doesn't really matter what temperature it's at, but it's important to understand that the temperature is evenly distributed. Heat is evenly distributed. And at the bottom of this lake, we've got a little fish. He's just swimming around. We could name him Fred if we want. And Fred is going to burp. Fred burps. And there's a little bubble which he emits. Our question is, what happens to this bubble? We've got a few options. Maybe the first option is that it just sort of stays the same size all the way up the lake and then emits the noxious fumes of Fred's burp at the top. 2, maybe it gets bigger. Maybe the bubble gets bigger, maybe not this big, but bigger. Or 3, maybe the bubble gets smaller. Maybe it gets so small that it's infinitely small by the time we reach the surface of the lake. And so to answer this question, to figure out which one of these paths the bubble of Fred's burp takes, let's examine this question in greater detail. And let's look at sort of a little force diagram, if you will, if you've studied physics, of the bubble, both at the bottom of the lake and near the surface of the lake. So first of all, let's take a look at the bottom of the lake. And so we know, or I'll tell you if you don't know, that water exerts a force on anything that's sort of within it, inside of it. And so this water is going to exert pressure, or force, on all sides of the bubble. And that pressure from the top and from the bottom is actually going to be equal to the weight of all the water that's on top of the bubble. And so if we're at the bottom of the lake, there's going to be a whole lot of water above the bubble, and so there's going to be a whole lot of force, a whole lot of pressure pushing down. And there's a little law in physics that says the force pushing down on something in water is equal to the force pushing up. And so there's going to be a whole lot of force pushing down and pushing up on this bubble, so a lot of pressure. What about near the surface? Well, we're still going to have pressure on the sides, we're still going to have pressure from the top and bottom, but there's not going to be anywhere near as much pressure or as much water pushing down on the bubble from the top. It's just so much closer to the surface, and so that force is going to be significantly smaller when the bubble is near the surface than when it's far away from the surface, when it's at the bottom of the lake. What can we conclude from this? Well, if we've got a lot of force pushing in, then something is going to get smaller, right? If I try and compress a balloon that doesn't have that much air in it, I can make it smaller. If there's not a lot of force, not a lot of pressure being exerted on a bubble, well, it can get bigger. And so we see that if the pressure decreases, we've just said that pressure decreases when the bubble is near the surface. We can also say that pressure increases when the bubble is far away from the surface. We can see that the bubble is going to get bigger. So volume is going to increase because the force on the outside of the bubble is decreasing. So we can conclude that the second option is going to be what happens in reality. The bubble is going to increase in size, sort of marginally, not this much. It's going to increase in size as it moves up the lake because the force, the pressure of the water being exerted on the bubble is going to decrease. And it's important to remember that this is all happening at constant temperature. And so now we can summarize Boyle's law. We can say that at constant temperature, and this is sort of verbatim what Boyle's law states, at constant temperature, and remember we just defined the lake as being at constant temperature, the pressure of a gas is inversely proportional to its volume. What does this inversely proportional mean? All it means is that when we increase the pressure of a gas, we're going to decrease its volume. So increase pressure leads to a decrease in volume. And then you might understand that we can just flip this equation. We can say that an increase in volume at constant temperature yields a decrease in the pressure, in the force exerted by the particles of the gas on the outside of its container, in this case the bubble. And so to help you remember this, we can actually draw a little graph and see what a plot of volume versus pressure is going to look like. And I can tell you that it's going to look something like this. It's going to look something like this, and it's going to increase in that direction and decrease in that direction. And this sort of makes sense. So as we move from left to right, we're going farther along this axis, along the pressure axis, so we're increasing pressure. And as we move up, we're increasing volume. So as we move up, we've got to move left to right on this graph. And so as volume increases, pressure is decreasing. To move down, to decrease volume, we've got to move to the right, and that's going to increase pressure. So we can see that pressure and volume are inversely proportional, and a final way to state that equation quantitatively is to say that P times V is equal to a constant. And so that when we get, say we're plotting volume in this case, volume is a function of pressure, we can solve V is equal to a constant over P, and that 1 over P is going to yield this kind of the shape of a graph. And so there are a lot of different ways to remember Boyle's law. I like to sort of think about the bubble analogy and think about pressure and volume in terms of sort of increasing size of bubbles in lakes, but you can remember it however you will. So that's Boyle's law. Now let's take a look at Charles's law. And Charles's law is going to take a look at two different quantities. We're going to hold pressure constants. Maybe that's important. I'll write up here. Pressure constant. And we're going to take a look at temperature and volume. And to do that, we're going to take a look at two different balloons, or maybe the same balloon on different days. Balloon 1 is being exposed to the sun on a really hot day. Balloon 2 is being exposed to the elements on a really, really cold day. As you can see, it's sort of almost snowing here. The question is, what's going to happen to the volume of these balloons? Over here, we're increasing temperature. Over here, we're decreasing temperature. And we want to see how the volume of the gas of the balloon is going to change as a function of temperature. And this is pretty obvious, but we know that in a cold environment, balloons shrink, and in a warm environment, balloons expand. Why is this? Well, let's take a look at the inside of a balloon. Within the balloon, you've got all these little gas particles. And when we increase the temperature, these gas particles are going to move faster. Whenever you give something more energy, temperature is just energy, you're going to make it move faster. And we'll actually take a look at that again when we look at the kinetic molecular theory. And so because these gas particles are moving faster, they're going to collide. Maybe we can blow this up here, this little wall of the balloon. That's pretty poor drawing, but you get the idea. They're going to collide. These gas particles are going to collide with their container more often and with greater force. So if I'm a big truck moving into a wall, I'm going to exert more force on that wall if I'm moving faster. And similarly, these gas particles are going to exert more force on the balloon if they're moving faster. Conversely, if we take a look at the sadly shrunken balloon, we see first let's blow it up here. We see that this is the wall of a container. This is the wall of the balloon. We see that the gas particles inside the cold balloon aren't moving that fast. They certainly have some energy, but they're not colliding with the walls of the balloon as much or with as much energy. It'd be like sort of hitting a brick wall in a little Mini Cooper at 2 miles an hour. You're certainly going to feel a little bump, but you're not going to transmit that much energy because you're not moving that fast. And because they're not even hitting the container of the balloon very often, they're not going to exert a lot of force on the outside. And so this is going to shrink the balloon. And so to maintain constant pressure, because remember pressure is constant, we've got to increase the volume of this balloon so that the number of collisions is decreased to go back to the baseline it was at our initial state here. And to maintain constant pressure over here, we've got to shrink the balloon, because when we cool down the balloon, we're decreasing the number of collisions, and to maintain constant pressure, we've got to increase that again. So we're going to decrease the volume of the balloon. So over here, we've got increased volume, and over here, we've got decreased volume. And so we can, again, just as we stated Boyle's law, we can state Charles's law in terms of a nice little sentence here. At constant pressure, so remember that's important, we're always keeping something constant. At constant pressure, a gas's temperature and volume are directly proportional. And you can remember this as when we heat something up, heat a gas up, it gets bigger. And when we cool it down, it gets smaller. And again, just like we did with Boyle's law, we can draw a little plot. Remember, Boyle's law was sort of this inverse 1 over x curve. The volume temperature plot is going to be a much more familiar to you. It's just going to be a straight line, a linear curve. Why is this? Well, as we increase temperature, we move to the right on the x-axis. We want to increase volume as well, so we're going to move up. And if we want to move down, we want to decrease volume, well, we're also going to have to decrease temperature. We're going to move to the left. In a way, again, remember how we stated Boyle's law quantitatively, we can also state Charles's law quantitatively and say that if volume and temperature are directly proportional, V over T is going to be equal to a constant. You can think about this in two ways. First of all, just take an arbitrary system. Say we've got a volume of 5 and a temperature of 5 arbitrary units. Well, our constant is going to be equal to 1. What happens if I change the volume? If I double the volume to get 10, my constant still has to be 1, so what am I going to have to do to the temperature? Well, I'm going to have to double that as well. So whenever I increase volume, I've got to increase temperature to maintain this constant. And so that's why whenever you divide two quantities together and set them equal to a constant, you're just expressing that they're directly proportional. Another way to think about this is if we're plotting volume as a function of temperature, we can just solve this little equation for volume, and so we get V equals constant times T, and whenever you have V equals something, that's going to be a linear curve, and so the slope of this line is just equal to the constant we've described over here. So just to recap, Boyle's law says that pressure and volume are inversely proportional. P times V is equal to a constant. Charles's law says that temperature and volume are directly proportional. V over T is equal to a constant. And we'll take a look at some further gas laws in the next video.